Welcome back, everyone, to episode 3 of Chasing Space. I'm your host, Brendan Swanwick, coming in with another topic that I think is totally worth listening to, and something that may not be too unfamiliar to you. Back on Thursday, June 6th, 2024 at 8:50 a.m., we saw yet another integrated test flight of SpaceX's new Starship vehicle. The Starship vehicle has probably been all over your newsfeed in the past several years with regards to space-specific news, just because it is such a daunting, unbelievably powerful, and revolutionary rocket. This launch was something that I found fascinating, but the real fascination that I got caught up on was in actually their previous launch, their Integrated Flight Test 3, which occurred on March 14th, 2024, so around 3 months prior. The main goal of this launch, and actually all their previous launches, was to demonstrate re-entry capabilities of both the first stage, the Super Heavy booster, and the vehicle itself, the Starship. So circling all the way back to the first integrated flight test, IFT-3, which I'll call it throughout this, the company shared several important firsts that they achieved beyond their primary objective of reaching orbit and some re-entry capabilities. So some notes were that they successfully completed a second stage burn with the Starship vehicle. They had a full burn of all 33 first stage Raptor engines powering the Super Heavy booster, which we did not see in the first or second test throughout the entire test. We saw a successful hot staging to separate Starship from the booster. Hot staging being a mechanism to separate the first stage and the Starship once the Super Heavy was depleted and Starship was appropriately positioned to enter orbit. And then an incredible series of footage from the event. If you haven't had a chance to check this out on YouTube, or any of the flight tests for that reason, you absolutely should. What they did is all of their cameras and all of their live feed capabilities were connected to, you guessed it, SpaceX Starlink, which really allowed them to get some incredible live views of re-entry, which we've really never seen before from a vehicle. Among all the excitement of all of these different things going on, the different first stage Raptor engines firing up, the Super Heavy booster streaking through the atmosphere when it was coming back down, piercing through clouds, it was super cool. There was also something else that happened that most people didn't catch, myself included actually, at the first live stream watch, and definitely did not receive its fair share of buzz. So, at approximately T plus 12 minutes, there was a unique call out. Quote, PEZ door is opening. And then at T plus 16 minutes, you could see a large, slim door visibly open on the live stream, vapors from inside the rocket spewing in and out. And then at T plus 28 minutes, we hear PEZ checkout's complete, doors closing, which can also be seen on the live stream as well if you look close enough. Keep in mind that between T plus 12 minutes and T plus 28 minutes, this is when the Starship vehicle was in orbit. Most people really weren't watching the stream at this time since it was essentially just elevator music and occasional shots of the Starship, but this was pretty monumental in my case. This inconspicuous opening and closing of a door to many doesn't really correlate to some huge shift in existing technology or some massive new revolutionary idea. But there really is a lot more significance than what meets the eye to the Starship PEZ dispenser. So for some context, if we circle all the way back, starting in quite literally October 4th, 1957, following the USSR's launch of Sputnik, widely considered one of the first satellites, nearly all the payloads integrated on a dedicated launch vehicle since then have all been deployed using a method called fairing separation. So fairing separation is essentially a mechanism that consists of encapsulating the payload, which is in most cases a satellite, inside this large cone cylinder shaped medium at the top of a launch vehicle, at the top of a rocket. So the fairing itself serves to protect the payload against all the intense dynamic pressures and heat that they experience during the launch. And then once they reach whatever their target altitude and inclination is, the fairing will do something called jettison, and this is separating into two longitudinal halves off of the rocket. Think like a clamshell separating its two halves and floating away. Nominally, these two different halves will re-enter into orbit and burn up. SpaceX has actually begun to recover their Falcon 9 fairings, but most just end up burning up in the atmosphere. And then at this point, whatever payload was being shielded by the fairing is now exposed to space for its separation and deployment. If you want to see this in action, there's plenty of videos on YouTube. There's a bunch of different companies that have some videos of this, SpaceX included, Rocket Lab. I believe ULA has some as well. And this method has an abundance of flight heritage and proof of success. But it's not really in the question right now for Starship. So if we think about the goals of what they want to accomplish, right? If you ask Elon Musk what he wants, he's going to say, we want to get this vehicle to Mars and back and reuse it. It wants to be full reusability. So he has complete horse blinders on these goals, right? He wants to take out all the engineering noise of little intricacies that may hinder these exact goals. So think ultimate goal, reusability, driving design. So they really don't have the engineering bandwidth to come up with massive new ways of releasing payloads through fairing separation. The Starship is not designed for that right now. But on the same breath, we're doing these integrated flight tests. We're doing Block 1 vehicles. We're probably about to start Block 2 vehicles soon with anywhere between 150 and 200 metric tons of reusable cargo. So coming up and coming back down. SpaceX needs an alternative, right? We have all this cargo space and it's going up empty. We should use it. So what they devised was something called the PEZ dispenser. And this draws inspiration from what I hope everybody listening recognizes, the childhood candy dispenser called PEZ, where it usually has a little animal or some type of cartoon character on the top. You flick the head of it back and a little PEZ candy comes out where the mouth would be. We've all grown to love this from childhood, and clearly Elon did as well, and drew inspiration from the mechanism itself on Starship, deriving its name. So the relevance to this candy dispenser is actually that the same mechanical concept applies. All the payloads inside of the Starship PEZ dispenser are arranged in a stack, just like the candies would be, inside the Starship volume, and they're dispensed through this door, either individually or in pairs of two. It's unclear right now. Currently, the only payload in work for this deployment is the SpaceX Starlink satellites. Here's actually a clip from the Everyday Astronaut when he took a tour of the Starbase, discussing this design concept for around a minute in 2022. Keep in mind there will be a bit of background noise just due to being in Starbase and work going on around Elon while he was chatting about it.
I mean, it's just, like I said, it's not going to blow your mind here, you know. It's basically, it's like we call it the PEZ dispenser. And it's kind of like that. It's the Starlink satellites are, you know, in this rack, which looks like a friggin' PEZ thing, because they're like, you know, kind of like rectangular, just like a PEZ, and they're stacked inside the nose cone, inside the fairing, and since they're low profile, we only need really a small door. With a small door, we can use pressure stabilization, like we can retain pressure in the fairing, so we can at least partially pressure stabilize the nose cone or fairing.
All right, so far we've developed this door to be some large, slim door for, as Elon said, pressure stabilization inside the fairing that is going to be used initially to deploy Starlink satellites. So up until this point, we've seen deployments of Starlink satellites, which seemingly is every week, whether from Vandenberg Space Force Base or down at the Cape, from their Falcon 9 vehicle. But the V2 model of Starlink is not going to be very feasible for the Falcon 9. So they're due for a large hardware upgrade, which is known as the V2 model, and they're growing to a huge size of 6.4 by 2.7 meters. And it's going to be around 1.25 tons. Just for comparison, the V1 is 660 pounds. So a quarter of a ton. And then due to the constraints of this Falcon 9 payload capacity, it's not a feasible solution to be a V2 specific Starlink workhorse. So designed to these new dimensions, you'll see that the PEZ dispenser opening, think like a massive mailbox, is a slim 0.8 meters tall and then 7.3 meters wide, which is just large enough to create this little slot for the V2 Starlinks. Another unique element of this is thinking about the fact that there is quite literally a door on the side of a rocket. And for all the mechanical engineers and structural engineers listening, this sounds like an absolute launch load disaster. So to itch that part of your brain, in order to compensate for transferring all these launch loads around this massive door, very slim but still very large, 7.3 meters, what they did was around the opening and windward side of the Starship, all the material is double plated, which is similar to adding a door frame to a home. You can also see, if you look close enough, there's additional supports, including a bunch of RBF struts, removed before flight struts, on the exterior surface, and then an additional 20 internal stringers. We don't know much about the dispenser itself. There is some speculation that it is thought to support up to 40 Starlink V2 satellites in that stack configuration. We'll call it the PEZ configuration. And it's also not entirely clear at the moment how this mechanism functions in detail. However, it was said by Elon that it would be largely motivated by existing pallet stacking technology. If you'd like to read a really fantastic technical deep dive on this door and the PEZ dispenser, I recommend an article. You can find it on ringwatchers.com. It's called The PEZ Dispenser, Starship's Payload Deployment System. It's around a half an hour read. It is absolutely fantastic and dives into everything we know about the dispenser so far. So far, we've talked about Starship, we've talked about the dispenser, we've talked about the door, and we've talked about Starlink. But why is this so important? Why is this something that's worth talking about for 15 minutes? Why is this worth listening to on your commute to work? Although it's currently designed specifically for Starlink satellites, the future implications of success of this deployment technology is massively important for the entire satellite economy. Currently, there definitely is a rapidly growing interest in the space industry for small satellites. Microgravity-based companies that are all exploring methods to perform tech demonstrations of whatever the company is pursuing from a technical perspective. So in order to do so, for the past 20 years, many companies will opt to use small, relatively inexpensive satellites, such as CubeSats, which think the size of a shoebox, or microsats, think a small refrigerator, in order to test these. By doing this, by using these small form factors, they can demonstrate their products' viability in a relatively cheap and quick way. And whether this serves to raise additional capital for proving your technology for a small startup or increase the likelihood of landing a government contract, proving the technology's worth is critical for a lot of these small companies, and there are a ton of them in space right now. Unfortunately, if you look at the geometry of a shoebox or a small refrigerator, and then you look at the geometry of any rocket, there's going to be some incongruencies. And they really don't organically arrange well when they're stowed with other payloads in a circular or conic volume of a launch vehicle. If you ever look inside of a bandwagon or a transporter mission for Falcon 9, which is their primary medium for rideshare, you can also look at Firefly's most recent Flight 5. You will notice that all the different payloads, whether CubeSats, picosats, nanosats, microsats, all the sats, all the different types of payloads, will be configured to a large, for simplicity's sake, cylindrical column in the center of what would be the fairing volume. So at the top of the rocket, think a large column, and on the column There's going to be different size plates. They're considered full plates, half plates, quarter plates, all configured radially around this column where the different payloads will attach themselves. Rocket goes up, enters appropriate altitude, inclination, fairing separates. These all deploy. But again, if you ever look at the pictures of this, it does not, you can tell visually, it's just not organically stacked. It's not designed for the circular volume of a typical rocket fairing. Implicitly, we're going to see, due to this challenge, the size of these different types of satellites and payloads being naturally restricted. Specifically, their surface area is restricted. So in order to accommodate, we are starting to see several companies beginning to design to the fairing volume of rockets, maximizing their surface area, which is super important if you have optical payloads, sensors, solar panels, patch satellites, antennas, so on and so forth. Additionally, it's pretty intuitive that the more you can fit, the more you can launch. Especially enticing for companies interested in any constellations or swarms, which are typically telecommunication satellites. You can actually see this deliberate effort in a lot of new communication sats from startups and government agencies. Some examples right off the top are going to be the Aerospace Corps and their DISSAT concept, which they've been working on for 3 to 4 years. The Chinese Liaojiang 3 experimental comm satellite, also circular. The SpaceX Starlink, naturally. Link Global, their satellites as well. And then the AST Space Mobile Blue Walker 3. These are just 5 out of, I'm sure, dozens of different examples of small satellite companies starting to take on this new form factor. Instead of being large and rectangular, they're flat, wide, mostly circular or a large flat square in order to stack well in these types of vehicles. So, to connect the dots, contingent upon a significant increase in launch frequency and success, there very well may be a new dispenser standard compatible with the Starship vehicle to accommodate these payloads for deployment. On top of that, to add to the attraction of this potential medium for commercial space and government payloads, and pending significant success and launch frequency, Starships are going to be a hell of a lot cheaper than any other launch vehicle on the market. The typical way to measure this is cost per kilogram. That's what is used in industry. I don't love this metric because there's way too many independent variables to really determine if this is accurate or not. But for the sake of simplicity in this episode, we'll chat it. So the cost of per kilogram of Starship is estimated to be anywhere in the range of 10 to 20 times cheaper than the current sticker price for available launch vehicles today, which is Starship's $200 per kilogram, US dollars, versus $3,000 per kilogram in the average launch vehicle. For a little bit more context, just if you're curious, here are some of the estimated current day commercial vehicles in the U.S. from the Government Accountability Office and their associated cost per kilograms. And again, you have to keep in mind there is a laundry list of variables that influence these pricings, including the payload types, payload unique hazards of the rocket, desired orbit, launch cadence. All of these different things influence this metric. Talking about some private rockets in space industry, the SpaceX Falcon 9 is around 2,864. Firefly Alpha is 9,600. Same with Relativity's Terran R. The ULA Atlas V is around that same metric, depending on orbit, of anywhere from 9,500 up until almost 17,000. Rocket Lab Electron is set to be around 25,000, and then ABL Space Systems RS-1 is going to be 12,000. Just because we're on the topic, let's talk about some international government agency vehicles. So the Indian rockets, the ISRO GSLV is going to be anywhere from 6,000 to 10,000. The PSLV is 8,400. The Chinese CALT Long March 9 is 3,000. and then their GA Long 3 is $12,000. And just to wrap up the conversation, for historical purposes, the U.S. Space Shuttle and the Space Shuttle program, the average cost per kilogram was $14,186. So I just tossed a ton of numbers at you, but compare all those numbers to what could potentially be $200 per kilogram with an effective, frequent, and successful Starship launch vehicle. And the simple takeaway is just that. Given compatible launch parameters, it has the ability to be incredibly cost-effective for payload developers, which in turn is incredibly influential for them to start adhering to their deployment system if SpaceX decides that it is in their best interest to open up the PEZ dispenser technology to other payload developers throughout the space industry beyond just their own internal Starlink satellites. And that really is the big question. Will SpaceX be interested in accommodating other commercial and quote-unquote appropriately dimensioned payloads beyond Starlink for the PEZ deployment? Or will they continue to design exclusively for Starlink, keep hammering the same PEZ deployment technology, keep hammering the re-entry capabilities of Starship to accelerate their progress towards that public-facing goal of 42,000 Starlinks in their mega constellation? So at the time, we spoke with Gwen Trotwell, the president of SpaceX, and she made it very clear at the satellite conference in DC back in March of 2024 that SpaceX would not be deploying any Starlinks during integrated flight test floor. And they were correct. We did expect to see some additional PEZ door checkouts, but we didn't get any on IFT4. I would expect in IFT5, which should be coming up soon, we actually saw just yesterday on Tuesday, July 9th, that they rolled their first stage Super Heavy booster out to the pad. And I would love to see potentially a full door actuation or some Starlinks on board. I would imagine that we're not going to get any Starlinks on board because they're just really hammering, trying to get the vehicle down and get it re-entered and get it safe, get the Super Heavy onto the chopsticks so they can start pushing forward with Block 2 vehicles. SpaceX certainly has a ways to go before all these different hypotheticals I tossed at you are realized. However, when that day comes, I really wouldn't expect nothing less than a wave of new opportunities, especially for satellite developers, payload developers, and even companies that want to complement this transformation in deployment technology. I hope everyone listening, whether in the space industry or not, learned something fun today about the SpaceX Starship PEZ deployer. It's certainly worth paying attention to, and definitely keep an eye out when you tune in for SpaceX's Integrated Flight Test 5 to see if they do a little internal view of their fairing volume to see a door open. Thank you all so much for listening. This episode has been super fun to research. Make sure, if you have the opportunity, to like and give me a review on Spotify, Apple Music, or whatever podcast player you're listening this to. And I look forward to talking to you all soon. Take care.